Hola, chaps. Let's learn.
Hola, chaps. Mr. Turk here. This is primarily for CP Physics. Yesterday, during our Google Meet, we did a calculation of Coulomb's law for 3-point charges. So here I am working to a similar example to what we had done yesterday in our Google Meet. I have 3 charges. They're in a straight line. The first charge, labeled A, has a magnitude of 47 microcoulombs, and it's a positive charge, so it's made up by removing electrons from an originally neutral object. 10 centimeters off to the right of it, charge B has a charge of 20 microcoulombs. Again, a positive charge, and I remind you that micro means 10 to the negative 6. Go an additional 20 centimeters to the right of B, and you get to charge C, which has a charge of negative 15 microcoulombs. And the challenge is calculate the net force on any one of these 3 charges. And by the way, it's going to be a different value for each charge. It depends on your point of view. The equation to use is Coulomb's law. The electric force between any 2 objects is equal to the product of Boltzmann's constant K times charge Q1 times charge Q2 divided by the distance from the center of one charge to the center of the second charge squared. Now, as you look at this, you might wonder, well, what do I do for 3 charges? Should I just multiply it times Q3? And the answer is no. We don't have an equation for dealing with 3 charges simultaneously. So what we have to do is a process of first identifying which one of the charges do we care about in this particular problem. Do I want to know the net force on charge A or B or C? I'm just going to randomly pick charge C because this is kind of what we did yesterday. And I want to calculate the net force acting on charge C. So let's look at the situation geometrically. C is a negative charge. A is a positive charge. Opposite charges attract. So they're going to pull towards each other. A is going to pull C to the left. From the point of view of A, C is going to pull A to the right. So you need to look at the geometry of the problem and adopt a point of view, just like when I'm talking to you, to me, I go that way, and from you, you go this way. So, point of view. Then shut off charge A, and I've been ignoring charge B. So now turn on charge B and consider what effect will it have on charge C. Charge B is also positively charged, the opposite sign of C. So just like A, charge B is going to have the effect of pulling charge C to the left. And of course, from the point of view of charge B, charge C is pulling charge B to the right. So these are vectors when we talk about forces. That means it has a magnitude and a direction. Now, I've simplified this and I've put it all into a straight line. But in a proper CP physics course, at least in the old days, we would have this a 2-dimensional problem where one of the charges would be up here or down there, and then you'd have to take into account the angles and use Pythagorean's theorem a lot, and more math than apparently you want to do these days. So I'm going to go through step by step and work through this calculation. Go ahead and leap ahead of me at any time and just wait for me to catch up to you. I am going to shut off charge B, leave charge C always turned on because that's the one whose point of view we're adopting. That's the one where we want the answer. And then one at a time, go through all the other charges, turn them on, plug them into the equation, calculate the net force, and keep track of it. So charge B shut off, charge A turned on, charge C always left on, and I plug that into Coulomb's equation. So the electric force between A and C, and and in particular, the force exerted on charge C caused by charge A is going to be equal to K, Boltzmann's constant, which you should have on your reference sheet. I remind you that K is 8.99 times 10 to the ninth power newtons, meters squared per Coulomb squared. And with those units, when you plug it into the equation, the coulombs will cancel, the meters squared will cancel, Coulomb squared will cancel, and you're left with an answer in units of newtons. The units will always work correctly for you. So charge A is 47, and on your TI or equivalent graphing calculator, you should go 47 second EE is the correct way to put in exponents, not this times 10 caret stuff. Second EE, micro means -6, so you would hit the exchange key. That is on a TI that is to the right of the decimal point, at the bottom of the calculator, that's the exchange key. 6, meaning this is 47 times 10 to the -6 power, and that is the value of charge A, or Q1. So 47 microcoulombs. I, of course, am just going to write it as microcoulombs because I know what to type in, times charge C, and I'll go ahead and write that as -15 microcoulombs. And you know that means on your calculator, you type exchange key 15 second EE exchange key 6, and that will give us -15 microcoulombs. Divide by, and here's a common mistake made by students. They'll look at this and say, oh, its position is at 20 centimeters. But where's the origin? The origin is way over here where A is, although I didn't mention that. It doesn't matter where I place the origin. The real question is, what is the distance from the center of charge A to the center of charge C? And the distance is, well, first I went 10 centimeters to get to B, and then I went an additional 20 centimeters to get to C. I tried to suggest that on this sketch here, that this is twice that, a little short. So the total distance from A to C is actually 30 centimeters, not 10, not 20. I don't put them in units of centimeters. So of course you've memorized the Greek prefixes by now, and you know that a centimeter is 1/100th of a meter. So if I have 30 centimeters, that means I divide by 0.30, and it's squared. So on a TI or equivalent, you would hit the X squared button, enter, and you should now get the answer. If you haven't stored K into your graphing calculator memory, I remind you, you would type that one in as 8.99 second EE, 9, store, alpha, and then pick some meaningful letter that will help you remember that this is Boltzmann's constant. No, don't pick B. Pick K, for example. Enter. And so now, anytime that you need that constant until you change the value of K, you would type alpha K, and it will pull this value out of your calculator memory and plug it into your current calculation. So what I type in on my calculator, now that I've done that, is I turn it on and I go alpha K 47 second EE minus 6 times exchange key 15 second EE minus 6 divide by 0.3 x squared, enter. Or and you can almost read that. So I get an answer that says the electric force caused by charge A acting on charge C is negative 70.4 newtons. So there's two interpretations that you have to carry on here. The first interpretation is a minus sign in Coulomb's equation means they attract, that they're opposites. Opposites attract, and that means I have a positive charge times a negative charge, The distance squared is always positive. Boltzmann's constant is always positive. So the only time that you get a negative force out of Coulomb's law is if they are opposite charges, a positive times a negative times a positive. So a minus sign means they attract. Of course, that means that if it were a plus sign, it would mean that they repel. So minus sign means they attract. If it were a plus sign there, and it's not in this case, that would mean that they're pushing apart from each other. So that's one interpretation. Now, the second interpretation is based on the geometry of the problem. Here we're all at charge C, and we look off to our left, and that's the direction to charge A. Charge A is to the left of charge C, and it's attracting charge C to the left. So that's the second interpretation. It's based on geometry. And I'm going to just write it down so it's a little bit explicit here. This means a force with a magnitude of 70.4 newtons is pulling C to the left. That's what you have to go through in this situation. Because if I ask you, great, what's going on at charge A? You would say, well, it's an attractive force caused by charge C, which is off to the right of charge A, and therefore this minus sign means C is pulling A to the right. And if you set up a coordinate system where to the right is positive and to the left is negative, that means you would indicate this force with a positive arrow pointing to the right, whereas over here at point C, from our point of view on this problem, this is an arrow pointing to the left in the negative direction. So I've done my first calculation. Again, what I've done is I always leave the charge where our point of view is from turned on. I shut off all other charges, and then one at a time, I turn them on, plug them into Coulomb's law, tally up the force, keep track of the direction, and work through the whole list. Now, this problem only has 3 charges. I long for the days when I give you 5 charges and they're two-dimensional, but here we go. I now shut off charge A, I turn on charge B, and I plug it into the equation. And what do we get? The force of electrostatic attraction or repulsion between charge B and charge C is equal to the product of Boltzmann's constant K times charge B, which is 20 microcoulombs, times charge C, which is still negative 15 microcoulombs, divided by the distance from the center of B to the center of C squared, which in this case is 20 centimeters, turned to meters, 0.20 meters, quantity squared. Now you practice this enough that you know that on your calculator, where it says 20 microcoulombs, well, first of all, where it says K, you're just going to go alpha K, assuming you put it into memory. For the coulombs, you're going to go 20, second, EE, exchange key, 6. And that exchange key is putting the minus sign in front of the exponent when you do it in that order. Please do not do the times 10 button for exponents. You will get misled if you do that. All right, beat me to the punchline. Beep, beep, beep. And I get negative 67.4 newtons. So again, the 2 parts of the interpretation. The first part means this is attracting to the other charge that was used. And now look at the geometry of the problem. Where is that other charge? Well, here we are on charge C, and we look off to the left, and we see charge B pulling us to the left. So this is a magnitude of 67.4 newtons pulling C left, pulling C to the left. Now we do some vector addition and we tally up the total combined force acting on these two charges. Well, the charge A is pulling C to the left with a magnitude of 70.4 newtons. Charge B is pulling C to the left with a magnitude of 67.4 newtons. And I suppose I could power up a calculator and go 4 plus 4 is 8, decimal point, 7 plus 0 is 7, 7 plus 6 is 13, and round to 3 sig figs, and I get 138 newtons to the left. That is the net force acting on charge C in this problem. 138 newtons to the left to 3 sig figs. Ta-da! All right, here, let's do the very same problem, same geometry, and only change our point of view. Let's go to charge A and calculate the net force acting on charge A. Same problem as before, I just want to change my point of view, and this time, what is the net force acting on charge A? Well, we shut off all charges except the one that we're interested in. So charge A stays turned on. Then, one at a time, I go through the list of all the other charges, take into account the direction, distance, direction is angle, distance, magnitude of the charges, plug them into Coulomb's equation, calculate the force, take into account what, is it a push or is it a pull, is it to the right, is it to the left, and then tally up the totals after I've gone through all the charges, one at a time. For charge A, you probably already calculated the answer for me. So the charge on A caused by B is going to be equal to K times 47 microcoulombs times 20 microcoulombs divided by the distance from A to B squared. Well, it's 10 centimeters, but you have to turn that into meters, and so that's 0.1 meters quantity squared. These are both positive charges. So watch what happens. I go turn the calculator on, alpha K 47 microcoulombs times 20 microcoulombs divided by 10 centimeters squared, enter, and wow, 845 newtons. See, K 47 microcoulombs times 20 microcoulombs divided by 10 centimeters entered squared. So 840 is a positive 845 newtons. Now, the geometry of this problem, so two things to it, right? The plus sign means repels and goes away from the other charge. Now, go look at the geometry and say, here we are at charge A, and this 845 newtons is caused by charge B pushing away from A, and A is pushing away from B. Newton's third law, for every action force, there's an equal and opposite reaction force. So these two forces are pushing against each other with a magnitude of 845 newtons, each trying to push the other away from it. From our point of view here on charge A, that means this 845 newtons is pushing A to the left. Now you're thinking, isn't the left direction the negative direction? And the answer is yes. Thank you for thinking that. So this is repelling A, and if you want to make it clear, right, pushing instead of pulling, right, pushes A left. Ta-da, meaning we're done with charge B. Now what? Well, we go through the rest of our list. So we always keep our point of interest turned on. We shut off the first charge we did. We turn on the next charge, which in this case is charge C. And now we do the calculation. What is the force caused on charge A by charge C? Now, I'll give you a hint. We already did this one. Ta-da! Look, the charge of C on A is the same as the charge of A on C, and that was the very first calculation we had done back in the first problem. We did Coulomb's constant, or Boltzmann's constant, times 47 microcoulombs times negative 15 microcoulombs divided by 0.3 meters squared, and we got negative 40.7 newtons. So I'm not going to calculate that again. it's an attractive force. And so I'm going to write down the second force is, I'm just copying and pasting, negative 70.4 newtons. And that minus sign means it is attracts. Okay, but what I really care about is that means it pulls A to the right, because we're on the point of view of point A, C is to the right of A, C is pulling on A. So this negative 70.4 newtons isn't negative meaning to the left. It means attracting to the right. And now when I calculate what is the net force on A caused by these two charges, you better be thinking, or draw an arrow. Look, if I were to draw an arrow suggesting the first force, it was a whopping 845 newtons pushing A to the left. So here I just do an arrow labeled at 845 newtons pushing A to the left. Now, in addition to that, at the same time, I've got charge C that is pulling A to the right, and this is not even 10% the length of that first vector. This is a little teeny tiny 70.4 newtons compared to 845 newtons, and it's pulling A to the right. How do I find the total? I do vector addition, which in this situation, I'm going to ignore, oh, well, this was attraction, that was repulsion. I'm going to look at my arrows and figure out what should I do with these numbers on my calculator. Should I add these two numbers together? Do I subtract one from the other? Which one do I subtract from which? Do I take the negative of both of them squared? What do I do? So the answer is subtract 70.4 from 845. And I suppose I could do that in my head, right? In fact, I'm going to round this to the nearest whole Newton. So 845 going off to the left minus 70 pulling it off to the right means the net force is 775 newtons, but it's a vector. You can't just give me the magnitude or I'll take points off. You have to tell me in what direction is the net force. So the net force acting on charge A caused by charges B and C combined effort is 775 newtons to the left. Ta-da! So I've just done an example problem like what we had done during our Google Meet yesterday. Some student had said, oh, it's a little blurry. Can I show how I did it? I'm sorry if this isn't clear enough for you as far as I brought the screen a little closer. Something just fell. Life is good. All right, do tell. I suggest that you do a practice problem yourself and let's just mix up a couple numbers, right? Okay, so let's say that charge A is, well, let's see, periods 3 and 4. So 34 microcoulombs, and I'll make it negative, and it's at the origin. And let's do charge B is 20 microcoulombs because we have to have the seniors and all these made up problems, right? And it's located, oh gosh, I don't know. Our classroom is 211. So it's at 211 centimeters. That's its position on the positive x-axis. And then finally, you know, just one more charge, right? So charge QC is something where I should flip a coin, which I don't have. Let me see if I can find one. I do. So heads it's positive, tails it's negative, and it came up positive. You might be able to see that. So it's positive, and this is from 1985. So 1985. Now, should I make it microcoulombs or nanocoulombs? Or even millicoulombs? Oh, let's make it microcoulombs again. And this time, instead of being 211 centimeters, I'm going to make it at a position not an additional distance. So it's at a position of 608 centimeters, being the other classroom I use at Cerritos High School. So calculate, please. And now I need a random number from 1 to 3, right? So which one of these shall we do? Probability, integer, random integer, 1 to 3, 1, 2, 3, 1 being the left charge, and the answer is the rightmost charge. Okay, so calculate, please. What is the net force acting on charge C? The problem stated once again. I suppose you can see all the information. I can read it to you once again, particularly if I go just a little bit more like this, right? You can just make it out. Okay, I have 3 charges. They're all in a straight line. The first charge I'm calling charge A, so it's totally different from the problem above it. It has a magnitude of negative 34 microcoulombs and is located at the origin of this problem. Charge B is a positive 2020 microcoulombs, yay seniors, and it's 200 and it's at position 211 centimeters along this x-axis. And charge C has a charge of 1985 microcoulombs. It's also positive, and it's at position 608 centimeters along the positive x-axis. Calculate, please, what is the net force acting on charge C? All right, you pause the tape, I'll do the calculations and resume, and we'll see what you get. All right, pause. Good, I'm glad you paused. So reminder for this problem, first charge is negative 34 microcoulombs, that's at the origin. Charge B is positive at positive 2020 microcoulombs at position 211 centimeters on the positive x-axis. Charge C is 1985 microcoulombs, which is 1.985 millicoulombs, and it's at position 6.08 meters. You should be starting to think of these conversions in your head almost automatically. Because A and C are opposite in sign, A is going to pull C to the left. So I put that in as a negative into my calculator. And charge B is positive, charge C is positive, like charges repel. So B is going to push C to the right. So I left that as a positive in my calculator, and I just entered it all at once. And here's my result, assuming I didn't make any mistakes. I got 2.27 kilonewtons as my net force. Overall, C is being pushed to the right stronger than it's being pulled to the left. So the net force is 2.27 kilonewtons to the left, up to the right. All right, ciao.